very good. And Gaia pretty much all that time then, or
yes, that's right. Yeah.
Yes. Preparations, and then of course the data. Fantastic. Yeah. So.
That's right. Yeah. So yeah, I was busy before launch, and I'm definitely even busier now.
Yes. Fantastic stuff. We've had so there've been some data releases already, and there's more to come, right?
That's right. Yeah. So we've had two full data releases, and we had this third one has been split into two. So it's been called an early data release, and then the full data release. So we are, and we're expecting to have 5 data releases in total. So we're just over halfway now.
Fantastic stuff. Yes, a good time to be having the talk.
Yeah.
Okay, so we'll wait another minute or so, and then start off. So yeah.
We've got participants rolling in all the time, which is
excellent.
Good afternoon, everybody. Yeah. And I'll have a look at YouTube as well when I can. It's recording on YouTube, so we've got a few on YouTube, not as many yet.
Okay, so we give it maybe another. Yes, it's just gone 2, so we give it another minute or so, and then start. Just to allow people to be a little bit late, because sometimes, yes, with the immediately post lunch thing on a Saturday, people are coming in. Okay, so we'll start in about 20 seconds.
Mark, I think you could do your video as well for the time being until after the break.
Okay, so probably we should make a start now. So hopefully everything's recording, and YouTube and Zoom are working well.
We're all going.
Excellent. Okay, so welcome everybody to the July meeting of the Society for Popular Astronomy, and today we're delighted to have a talk from George Seabroke, who's a colleague at UCL's Mullard Space Science Lab. He's just been telling us he's been there for about 11 years now, so time really flies. And George has been working on Gaia from before launch to now, so research associate working with us. And George is going to tell us today about the Gaia revolution. So go ahead, George.
Yeah, thank you very much, Andrew. Let me just share my screen. How's that?
Yeah, that's good. Full screen, perfect. Yeah,
fine.
Thanks. Yeah.
I'll just show off the fact I'm wearing the Gaia merchandise as well. I don't know if you can see that on the video. Yeah.
Yes, we can. Excellent. Thanks. Yeah.
So thank you very much for the invite. It's a pleasure to be here. Be here at home and speaking to you. Sorry to not see you in person. Maybe we can do that again when things are better. But so I'll be talking about Gaia, which is the spacecraft I've been working on for a long time, 11 years now at least, as Andrew said. And before I start, I'll say that Gaia is a very large collaboration. So I'm speaking on behalf of around 400 scientists, astronomers, software engineers, computer scientists around Europe, who are currently in a collaboration to process the data that are coming down from this amazing satellite. And prior to launch, there was a similar number involved in addition, in the form of engineers and scientists working on proposals to bring it to fruition. So it's been a large collaborative effort, as a lot of large science projects are these days. So this is on behalf of all of those people. So I'll start by showing you a video, but about Gaia. But let me just explain the title a little bit. So I'm going to try and convince you that a revolution is happening in astronomy, and that's being brought about by Gaia's fantastic measurements. So I'll be talking about many different aspects of astronomy that Gaia touches and is, hopefully, as you agree, revolutionising. But if there's a topic that I don't mention and it's your favourite topic, then there's a chance that Gaia it does affect it in some way, and it's just that I haven't had time to include it in this presentation. So please ask at the end if there's any of your pet topics that you'd like to hear more about. But please don't ask about individual stars, because there's more than 1.8 billion of them, and I don't know them all off by heart. So hopefully you can see this and hear this now. So this is a video that's been produced by the European Space Agency. So this is Gaia. It is a European Space Agency mission. This is the satellite itself. You can see technicians working on it. This is in French Guiana, just prior to launch. So that turret, the top hat bit there is about 4 meters, and the diameter of the sun shield is about 10 meters or so. The sun shield now has been folded up, and it's sitting on top of a Soyuz frigate, and it's being encapsulated there for protection during launch. And it's the so it's the same Soyuz, well, not exactly the same rocket, but the same heritage of rocket that put Yuri Gagarin into space. The same sort of size of rocket. So this is now outside in French Guiana in South America. So Gaia was launched back in December 2013. Here Gaia comes up on the lift, the harness being mated to the rocket, and you'll see technicians running around just before launch. This isn't actually how it happened, and nobody's that close when it goes off. And there she goes. So it launched very early in the morning, so it was really dark sky. So I was fortunate enough to be there. It wasn't the loudest of rockets actually, because it's only a medium-sized rocket. So I was hoping to be blown away by the sound, like watching a shuttle launch, which unfortunately I never saw. But it was still a wonderful experience to be there. So this is a picture of myself with Gaia. So this is Gaia already in space, and a colleague happened to snap me watching it go. So it's already over the South Atlantic at that point, traveling incredibly quickly. So I never actually got to see Gaia first to last, like you saw in the video there. The closest I got to was this moment here, with seeing his exhaust plume, which is in some ways a strange thing to say, but I wasn't involved in the building of Gaia, but I'll explain my role in a moment. So another video to help explain what Gaia is. So now we've launched, and now we're taking Gaia on up to orbit. So this is now a computer animation, but I did see the 4 rockets tumbling away as me standing down there by the beach, and then we didn't see the fairing blow away. It was too high at that point to see that. And so this is the frigate separating from Gaia. Interestingly, the Soyuz frigate failed on a telecommunications satellite in the launch after Gaia, and so the 1 billion euros that had been spent on Gaia could have been lost quite easily. And it was just a reminder of how precarious space can be. But fortunately, we were all fine. The sun shield opened up as well. That was quite a nerve-wracking moment, because the whole mission depended on that successfully opening up. And so Gaia took about a month to get to this point called Lagrange point 2. So this is a gravitational point so beyond the Earth, about 3 times further out from the Earth than the Moon is. And so it's actually going round the Sun in its own orbit. And Gaia spins every 6 hours. It's got 2 telescopes, which is why we've got these 2 beams here. So it's not actually firing out these rectangular lasers into space. These rectangular beams represent the line of sight of Gaia, of looking at the stars. So you saw there it was looking at the stars, and so its primary purpose is to measure stars in our galaxy to try and work out how our galaxy formed. So all the data is available on the archive. So I'd love to be able to show you some beautiful images that Gaia produces, but it's not that sort of mission. It takes measurements and it produces numbers. So in some ways it's more of a hard sell in terms of public outreach, but you better judge for yourself at the end of this talk how well I've done. So we were chatting with Robin just beforehand about the distance to Deneb, and so stars that are famous stars like that you can put into the Gaia archive. You can see my mouse here. We've put in the name Proxima Centauri, so the nearest star to our sun, and you can find out all the Gaia information that there is available on it. So that's a way to look up your favourite star. So as I said, Gaia just produces large tables of numbers, and if I was to spend 1 second on every star in this table, so we're just displaying just a few here, but the entire catalogue contains 1.8 billion rows, and if I was to spend 1 second on every star, it would take the talk would take about 30 years. So in which case I need to get going on that. So 1, 2, 3, 4. So I'm just I'd hopefully have received rapturous laughter for that one if we'd been in a hall all together, but I'm just going to assume that there was laughter for that joke and move on. So so this is a graphic informing about the data that came out in the latest data release, and this was called Gaia's early data release 3. So there have been 2 prior data releases to that, and all this data came out in December last year. And so you can see the numbers are, if you'll excuse the deliberate pun, the numbers are astronomical. They're not the largest catalogues of data, but it will certainly be one of the richest catalogues that has ever been available. So I'll go through some of these measurements to highlight what Gaia can do. So we have 1.8 billion positions, and I'll explain in a moment that Gaia is primarily an astrometric mission, which means it measures the positions of stars. And we've got 1.5 billion colours. So when I said that Gaia doesn't produce images, for example, like the beautiful Hubble images that are available, so that's not quite true. So this is an image from Gaia, and it is very beautiful. So this is of our Milky Way, and all 1.8 billion stars are represented in here. Or to say this is the colour image, so the 1.5 billion stars are represented in here, except this has been an image that's been constructed from the individual measurements. So we've taken the positions of the stars and the colours, and then within each pixel we've counted how many stars are there and the colour of those stars, and then coloured that pixel according to the aggregate of that information. And so in this way we can make images like this. And so you can see our Milky Way, the 2 fried eggs back to back, with the dust lane in the middle, and lots of other dust as well, and the small and the large Magellanic Clouds at the bottom there. So coming back to this graphic, I'll now explain really the revolution that Gaia is bringing in astronomy. So this is based on these parallax measurements, which is how we can directly infer distance to individual stars. So if you look on the graphic on the left here, so Gaia and the Earth are going around the Sun, as you know, and we know the distance between the Earth and the Sun, and we also know the distance between Gaia and the Sun. So it's about 1 astronomical unit. And then if we're looking at this star here compared to background stars, if we look at this star as Gaia or the Earth is going round the Sun, and then 6 months later we look at that same star, this nearby star appears to have traced out this ellipse in the sky because of the motion of Gaia around the Sun. And it's this motion, this apparent motion of the star in the sky compared to much more distant stars that allows us to infer the distance to the star. So we measure this angle here by seeing how the star moves. We can measure this angle here called the parallax angle, and then by knowing the distance between Gaia and the Sun and this angle, then we can infer from trigonometry what the dashed line here is, and that's the distance to the individual star. Now on the right hand side, this is being illustrated. Sorry, let me move my video was in front of the simulation here. So yeah, sorry. On the right hand side, you can see. So here's the Sun and the Earth, or Gaia, going around the Sun, and then here's a star that it's viewing. So now when the star is further away, you can see that in the top here that the star appears to be not moving very much compared to the background stars. And when the star is a bit closer to the Sun, I'm sorry, it's gone away again. Right, we'll start there. So when this particular star is further away from the Sun, you can see that it doesn't move very much. And when we're much closer, you can see that that star is moving much more. And so that means it's more and more difficult to measure this parallax angle the further and further away stars are. So we were able to measure the parallax of the nearest stars from the ground, so just by using Earth as our observing platform and going around and looking at the star. And the atmosphere didn't blur the images that much, so that we could measure the largest angles for the nearest stars. But if we want to measure stars further and further away, then we need to go to space in order to be able to measure this angle as it gets smaller and smaller as stars get further and further away, which is why the Gaia spacecraft is a spacecraft, and we had to go to space to get above the blurring effect of the Earth's atmosphere. So just to illustrate the capabilities of Gaia, the amazingly small angles that it can measure. So it does do repeat measurements. So typically it will measure any one star about 70 times, and so that can help with the precision. And the platform is built to be incredibly stable. And this enables us to measure this incredibly small angle here. So this is a very small fraction of a degree. So I'm not expecting you to really have any idea really what that means. I don't without an analogy. And so that the analogy is that the Gaia can detect angles which are as small as an astronaut thumbnail when they're standing on the moon. So I think this might be Buzz or Neil, I'm not sure which, standing on the moon. But Gaia, it would be capable of measuring the angle from one side of their thumbnail to the other if Gaia was on the Earth. And so that's an absolutely mind-blowing capability to measure such small angles. And so this means that Gaia can measure stars that are incredibly far away. And so we're able to measure quite a significant number of stars in the Milky Way. So I've mentioned that we're measuring the distances to more than 1 billion stars, which sounds a lot, but this is actually only about 1% of all the stars in our Milky Way galaxy. But still, it's the best that we can do at the moment with the technology we have, and that 1% is hopefully representative of the galaxy as a whole, and so we can start to infer how the galaxy formed from this incredible data set. So part of the reason for Gaia being able to perform so well is the detectors, so the eyes in the sky. So these are this is the focal plane of Gaia. So it has 106 charge coupled devices, or CCDs, if you're familiar with that technology. So these are effectively very large digital cameras all put together. And so when you count the number of pixels that it has, so it is nearly a billion pixels, or 1,000 megapixel camera. So this used to be the largest digital camera in the world, either on the ground or in space. But that's actually, so now we still hold the record for the largest digital camera in space. On the ground, that's actually been overtaken by a ground-based telescope called Pan-STARRS, which is on which is in Hawaii. So the reason, or part of the reason I'm able to talk to you about Gaia today is that the Mallard Space Science Laboratory, which is part of University College London, where Andrew and I are both based, so MSSL tested all of those digital cameras, and this is just a picture of some of that testing going on. This is a vacuum chamber, and you can see, you might be able to see, I'm going to get my mouse to work on this bit, but you can see the little blue square, that's one of the detectors in place, and there's 3 spaces around it, so 4 detectors can be tested at one time. And so all of those detectors passed through MSSL and were tested before being sent to Toulouse to be integrated into the spacecraft. I should also mention that the detectors are a British manufacturing success story. They were all designed and built by a company called E2V, who are based in Chelmsford. So have since been taken over by another company and are now known as Teledyne E2V, which was a US company. But at the time, it was I think a largely British-owned company, and they built all the detectors for Gaia and also Hubble. So if I come back to this graphic to illustrate the data that is available, I'll now talk about proper motions. So we have yet another video to illustrate proper motion. So we're just going to look at a small set of stars on the sky, represented by the dots here. And now we're going to follow them over quite a number of years. So this has been fast forwarding many thousands of years into the future. And these lines represent how the star is moving in the plane of the sky. And this is what we call its proper motion. So it's measured by typically a very small fraction of a degree per year. And so normally this motion cannot be seen with the naked eye. Is far too small to be seen, but with Gaia's fantastic technology, we can see these stars move very, very slightly and measure that motion. And so this was so the picture that you're looking at now actually made it onto the front page of the Times with an article about Gaia's early data release. So that was back in December last year. So the next movie I'll show you is going to illustrate how the stars move and how Gaia sees them. But because of Einstein's theory of general relativity and how that gravity bends light, this movie is going to illustrate how bodies in the solar system bend the light from the stars. And so if you want to know exactly where a particular star is in the sky, then we have to take into account this general relativity. And so this movie is showing, this movie has removed the effect of the sun, which is the most dominant effect on the light bending, as you might expect, because the light bending gets more with more mass. The scale here is at the bottom is down in the red is about 70 microarc seconds, which is an incredibly small angle. It's roughly similar to the angle that I showed you with the astronaut's thumbnail being viewed on the moon if you were viewing it from the Earth. And so these are incredibly small effects that the general relativity imparts on the apparent position of the stars. But because we know general relativity extremely well, we can remove this effect and thereby gain access to the true position of the star on the sky. And just say, so the main players in this movie are the Earth here and Jupiter here, although you can see all the other solar system planets playing a smaller role as they come and go. So this is the Earth going along, it's Jupiter. And so obviously this is a very time-dependent correction that's got to be made on all these measurements. But we know very precisely how all the bodies in the solar system move, and so we can, using general relativity, correct for this effect. Okay, so having removed the light bending effect from the solar system, we can look at how the stars are truly moving in the sky, and sort of the motion that is representative of how they're moving around in our galaxy. And so this graph here shows, it's going to zoom in on the plane of the sky. So amateur astronomers will recognize right ascension and declination there. So so that a star typically traces out this sort of helix shape, denoted by the solid line here, or and the dashed line. So the loop back in each case is the parallax that I mentioned earlier. So this is the effect of Gaia going round the sun and causing that star to trace an ellipse in the sky. And so that's what we see. And so we see that repeated as Gaia goes around the sun, and then around again, and then around again. So the next thing to point out is the dash line, the straight dash line going diagonally up. So this is the motion of the star. This is how we would see the motion of the star if we were standing on the sun, basically. So if we weren't going around the sun, we wouldn't get this parallax ellipse shape in the motion. We would just see the star moving along its path in the Milky Way. And so this is the proper motion, and so that's illustrated in the graphic in the bottom right there. So this is the motion that's perpendicular to the line of sight. And so when you put those two motions together, the proper motion, the dash line, and the dotted line for the repeating helix motion, then that will give you the typically how Gaia sees a star moving in the sky over time. So the solid line has got some kinks in it, and this is due to the apparent motion of the star as a result of a planet going around the star and actually perturbing the star's motion as seen from by Gaia. And so you can see it causes some funny little kinks along the way. And so Gaia, although it hasn't released any of this data yet, it will be able to fit for planet searching like this. And so this is yet another method for how you can find planets. So this is the astrometric method of finding planets. And if Gaia is just finishing its nominal 5-year mission, but if everything goes well and we make it to our 10-year end of mission, which is when the fuel on board will run out, then it's been predicted that we should be able to find 71,000 planets using this method. So which is an extremely large number, given that fewer than 5,000 planets have been confirmed as of earlier this month. So I've mentioned the proper motion there. So that proper motion can be so that's measured in fractions of a degree per unit time, but we can convert that to transverse velocity in more physical units, typically kilometers per second, using distance. So the parallax is measured, and we can convert the proper motion to a transverse velocity. But of course, stars aren't all moving in the plane of the sky. They're moving in all different directions, or at least components of their motion are moving in all different directions. And so their total velocity is in whatever direction it is. And we're just measuring, by measuring the proper motion, we're just measuring one component of that. And so the other component that we need to measure is the radial velocity. And this is the bit that I'm involved in. So my day job with a team of software engineers at MSSL is to process the data that comes down from Gaia's radial velocity spectrometer. So this data was part of the early data release, but wasn't included in the graphic here. So I'll go back to the previous data release where we had our large data release of radial velocities. So this was back in 2008. So you'll be able to see the little green sphere there. So we released 7 million radial velocities So that's 7 million stars with radial velocities, and at the time that was record breaking for being the largest radial velocity survey. So since then, a ground-based survey has actually just beaten us. Actually, they've just gone up to about 9 million. But we're in the process of preparing for the full data release, which is going to be available next year, where we'll boost our numbers up to about 30 million. And so the revolution continues in terms of the numbers of radial velocities that we'll be producing. So just to explain a little bit more about radial velocity. So in order to measure the radial velocities from stars, we need to split the light up into its spectrum. So white light passing through a prism gives rise to the rainbow array of colours, and so that's illustrated here on the left, and then on the right we have the electromagnetic spectrum. So your eye can see between about 400 and 700 nanometers, but we're measuring wavelengths a little bit redder than that. So they're invisible to the naked eye, but of course our detectors can measure the light. So this is what our prism looks like, which is quite pretty. And here's an example of a spectrum from Gaia's radial velocity spectrometer. So just to be confusing, the units have slightly changed, but it's in angstroms, but it's about 850 nanometers. So as I said, redder than the eye can see. So we measure the radial velocity by these characteristic lines in the spectrum. So these are the dark lines, or the absence of color that you would see in the rainbow of the spectrum. And these lines have been caused by typically, in this particular case, calcium atoms or ions in this star's atmosphere has blocked light from reaching us, and so we see an absence of light here. And so this line here forming an absorption line, so meaning light at these particular wavelengths have been absorbed by calcium ions. And so by seeing this characteristic pattern of lines, we know where these wavelengths should be if a star isn't moving. So if it's at rest, we know where they should be. And so by comparing those positions to the positions of stars that are moving, we can measure the radial velocity, a bit like the Doppler effect that you hear audibly with, say, a car coming towards you and then going away with you. The pitch changes. Similarly with light. So if the spectrum, if we see lines moving to the red end of the spectrum, that's a redshift or a Doppler shift, and we know the star is moving away from us. Or if we see a star moving towards the blue end of the spectrum, then we know that star's moving towards us. So as I mentioned, Gaia's produced a very large number of radial velocities, but just to put it in a bit more context, there's a funny historical coincidence that helps to put those numbers into perspective. So as we were talking about before, Robin was saying I actually died a while back, but this was actually my great grandfather, who was an amateur astronomer. You would have thought I'd better say that word by now. Who back in the late 19th century and early 20th century. So he was actually conducting, as he called it, spectroscopic observations of the motions of stars in the line of sight. And so he was, even though he was an amateur, he published his findings in these 3 papers. So you can see the numbers of stars that he was measuring were fairly small, although it was given that he was doing this all by eye and one by one, and actually quite a number of observations of those stars. It was fairly groundbreaking at the time. So it was one of the first radial velocity surveys that were being conducted, and there was also a rival radial velocity survey being conducted by the Royal Observatory at Greenwich. But both methods were doing it by eye, using a micrometer and seeing the spectrum being dispersed. So they would have seen those colours, and the black lines for the absorption lines. But it turns out that doing this by eye and using a micrometer just isn't accurate enough. And so, unfortunately, nearly all of these measurements are largely noise and actually incorrect. So I'm hoping that this isn't that fate is not going to befall me. Although, of course, some radio velocities will turn out to be wrong. For various reasons, and we have had feedback from the community, and and that's been useful in terms of improving our data processing, ready for the next data release. But so this chance historical coincidence I only found out about during my PhD when I happened to search the literature, and someone pointed out that I'd already been publishing many years ago. So now we've got the radial velocity and the Proffer motion. So that means we've got all the information we need to measure the space velocity of the star. So we've got all the information to actually work out how the star is moving. So as I mentioned right at the beginning of the talk, the goal of Gaia was to try and work out how our Milky Way formed. So I won't go into it into too much detail, but there are various components in our galaxy. So the thin disk is where the sun resides, and that's a thin disk, really the white of the two eggs back to back. And there's a bar and a bulge, which is the yolk. And there's a stellar halo of stars, which you can see faintly around, obviously the dark matter halo. And there's also a thick disk of stars, which is a bit like the thin disk, but as the name suggests, it's just a bit thicker. And so using these measurements from Gaia, we can change our frame of reference to measure those space velocities in these three directions here. So we have sort of coming out of the screen in the direction of rotation, there's Vy velocity, then we've got the vertical velocity coming out of the plane as Vz, and then towards the galactic center there's Vx. And so by measuring, by having this information for those 7 million stars for which you've got the radial velocities, and that's the full information on how the star is moving, then you can look at the stars in the Milky Way and plot them in this particular way. So on the x-axis is the rotational velocity, and then on the y-axis is a combination of the radial, so in towards the galactic center velocity, and the vertical velocity. And most stars live down in this blob, the blue blob, around 200. So that means most stars are rotating around the center of the galaxy. So this includes our sun, at around 200 kilometers per second, just going around in a nice circle. But some stars, which we didn't expect to see, didn't seem to have much rotational velocity, and they seem to form this blob here. And so we didn't expect to find these here. And so when computer simulations were ran to try and understand this, then you were able to produce quite a similar blob here. So this is the same sort of plot in the bottom here as in the top, except the simulation is showing that we've got some blue circles here, and it's even forming a little arc, a bit like above. And because this is in a simulation, then we can see how those stars ended up being in this particular part in the diagram. And so in this simulation that I'll show you in a moment, this illustrates how those stars came to be where they are. So we're looking down on the top of the galaxy, and starting from very early in the universe up to present day. And we'll see that what happens is, so we've got a very young Milky Way in the middle, and then this large galaxy, not quite as large as the Milky Way, comes in and starts being ripped apart by the Milky Way's gravity. and then and eventually gets completely ripped apart, and it ends up leaving stars that that have distributions a bit like this, except the spatially it's difficult to see unless this event happened very recently. You don't tend to see stars um, in configuration space, sort of physically clumped together. Typically, because this happened about 5 or 6 gigayears ago, those stars have been dispersed, but the memory of how those stars came to be is in their velocities, and so we can see that the stars that are from the simulation, the stars that are in red here, they end up being in that space in the bottom of the plot here and in the observational plot here. And so that in this way we can infer that the Milky Way was formed by this large galaxy, which has been called the Gaia Enceladus, sometimes referred to as the Gaia sausage, which I won't go into, and so really Gaia has done a large part of what it was intended to find out. So this was its goal was to find out the assembly history of the Milky Way, and this is a very large piece of the jigsaw that has already been found. So there's still a lot more to understand about this particular event and how other smaller events occurred to leave us with the galaxy as it is today. But this has already been a fantastic success of use of the data, and including the radial velocities that are helped to produce. And so this was a paper in Nature by Amina Helmi. So that was what Gaia was originally built to try and find out about how the Milky Way was formed, and it's been very successful in that. But when you're measuring the distances and the velocities of so many stars, there are many other spin-off science, much spin-off science that can be done. And so I'll just talk about some of my favourite in the next few moments. So unfortunately, I haven't been involved in any of these, but they're using the data that I've helped to produce. So I'm going to talk about close encounters, not of the third kind, i.e. we're not going to meet aliens, or at least not yet, and not in this talk, but I'm going to be talking about close encounters. So these are going to be encounters both of objects that we've sent out of the solar system and of objects that have come into the solar system. So this is a cartoon of the solar system. So I should explain that this is a logarithmic x-axis, and so the planets aren't really all bunched up nicely like this. The distances are getting larger and larger as we go towards the right. But so we're going from 1 astronomical unit at the Earth, and then we're already at 10 astronomical units with Saturn. And then 100 astronomical units takes us to the heliopause, to the edge of the solar system, and then several 100,000 astronomical units takes us to the nearest star. So that's Proxima Centauri, which is part of the Alpha Centauri system. So that's shown on the far right there. So first of all, I'm going to talk about what will be and what are interstellar probes that are probes that are going to leave or have left the solar system. So the first one is New Horizons, which I'm sure most of you have heard about. That's the one that sent back the fantastic pictures of Pluto as it flew by. So this one also went very close to this Arrokoth object. So this is an object in the Kuiper belt, which is a belt of objects further out than Pluto, but it includes Pluto in there. So I include this because Gaia's star positions were able to be used to help the New Horizons spacecraft actually fly close to Arrokoth. So it's so the navigation, obviously flying close to a body that's unknown, if you have very accurate star measurements, then you can do occultation measurements of when this object passes in front of stars, and knowing very precisely where those stars are, you can learn about the shape of an object. And so this was done with this object, and so Gaia helped New Horizons get fantastically close to this object. And then New Horizons, I think, will be going, possibly it'll be changing course and going elsewhere, but so it won't be going interstellar quite yet. But 3 objects that are going interstellar are so Voyager 2 at the bottom, Pioneer 11, and Voyager 1 at the top. So I've positioned these graphics roughly in the direction that they're heading. So Pioneer 11 is roughly going in the plane of the planets, and Voyager 1 above and Voyager 2 below. And of course Pioneer 10 is going in the opposite direction. So these are either just about to leave the solar system, or have left the solar system and are out into the interstellar space and going to who knows where. But with Gaia data, we can start to constrain where they're going and what they might meet. So one of the most interesting uses of the Gaia data has been to try and predict whether these stars are going to meet other star systems. So we've got 2 moving objects. We've got the spacecraft moving, and then we've got stars moving close to the sun and possibly coming quite close. So at the moment, it looks as though we don't have any very strong candidates for these space probes actually meeting stars and coming particularly close to them, and that's partly because of the limitation of the data. So although it's revolutionary at the time, with having the 7 million radial velocities contributing to the full knowledge of how these 7 million stars are moving, this obviously represents a small fraction of stars around. And so with the next data release next year, when we boost that number up to 30 million, then it'll be more likely to be able to, if we repeat the search again, we'll be more likely to see whether these 3 interstellar probes are going to actually meet another star system, and interestingly, if that star system was to have planets. Of course, this is all very far in the future, many thousands of years. But it's good to be prepared, and it's really, I guess, just a bit of fun. So this has been talking about objects that are leaving the solar system. So I'll next talk about objects that are coming into the solar system from outside. And so with the Gaia dataset, we can consider stars that are going to come close to our sun, and in particular perturb the Oort cloud. So this is labelled here at about 10,000 astronomical units away or so, and it's a large cloud of essentially comets that have been flung up there from the formation of the solar system, and it's interesting to consider whether stars are going to be moving and actually coming within the Oort cloud, because if they do, then they can gravitationally perturb these comets and fire them into the inner solar system. So it's possible that this is what happened with the dinosaurs. So the dinosaurs had a massive extinction level event about 65 million years ago or so, and it's possible that I think they think it's more likely to be an asteroid than a comet, but there is the possibility of asteroids also living in the Oort cloud, and so a star coming in to the Oort cloud 65 million years ago potentially sent in the asteroid that killed off the dinosaurs. And so using Gaia's dataset has been looked to see, has been searched for to see if we could see if there is a star that's responsible for coming into the Oort cloud and doing that. And there aren't any strong candidates at the moment. But as I say, with more data, then there is the possibility of testing this idea. Then looking forward into the future, this star here, using Gaia's data to see how the stars will be moving in the future, we can see that this particular star, Gliese 710, is actually going to come right into the Oort cloud in about 1.3 million years. So this is basically an early weather warning system for bad weather for in the inner solar system for comets. And so, potentially this is the extinctional level event that will kill all life on Earth if we don't do anything about it, or it maybe not. But it's interesting to look for this, and indeed with more data as is becoming available next year, we'll be able to search for more events and potentially events that will be happening sooner in time, and so giving us a bit of time to prepare. So another interesting, a new a field within astronomy is become these interstellar objects that have been found. So, oops, sorry, we'll come back. So this particular object, if I can pronounce it, it's Oumuamua. So this, sorry if I pronounced that wrong. This is so that's Hawaiian for messenger that's come from afar for the first time. So this is very apt, because this object is because it plunged into the solar system between the Earth and the Sun, as illustrated here, and then shot out again. So gravitational slingshot effect. But this object, and a debate raged for a while as to whether it was an asteroid or a comet, and I think they've ended up on the comet side of things, but that debate may still be going on, that this object has come from another star, has been ejected from another star system, and has been flying through space in the galaxy, and then happened to come across our solar system and then flown right through it and out again. So this was discovered back in 2017, I think it was, by the Pan-STARRS telescope, which I mentioned. So and that's on Hawaii, and hence the Hawaiian name. So this is a tumbling object about 100 meters long, I think it was, if I remember correctly, and it was tumbling in a very chaotic way. And so we can ask the question with this particular object, and this question has been researched in detail with the Gaia data, to say where could this particular object have come from. So because we know the trajectory of it into the solar system and then out again. So these 7 million stars from Gaia were searched through to see if there are any candidates, and there are candidate star systems from which this came, but no firm candidates. And so, of course, with a larger data set, then we can consider again where this object might have come from, and indeed where it might be going. So. Of course, so this was just the first interstellar object that we detected. I say we, not me. The group in Hawaii, and but of course these things have been raining through the solar system since the solar system began. It's just we're just starting to see them now. And a second one was found as well. So 2I for the second interstellar, and this was called Borisov. So this was actually discovered by an amateur astronomer from the Crimea. And this movie illustrates actually both of them coming through. So this was discovered 2 years later, the Borisov one. So that just shows you that this one went beyond the. So the orange line is Mars's orbit there. So this actually went through beyond Mars and then out again. And so the origin of the interstellar origin of Borisov has also been searched for, and there's a stronger candidate than the other one. But of course, it is just a candidate at the moment, and so we can as Gaia produces more and more data. So in particular, the radial velocities will hopefully get up to more than 100 million by the time we have our final data release in about 2030-ish, and so there'll be more and more stars to play this game with. So also excitingly, to do with this area of astronomy, there's a new European Space Agency mission which has been recently accepted as a mission to go ahead and build. And this is called the Comet Interceptor. So this is going to identify. So beforehand, comets are going to be identified, and this is going to go intercept them. I guess a bit like Philae with the asteroid, but it's going to and being out in space, if there aren't any, when it's got some downtime, if you like, and there's an interstellar object coming through space, then this mission could actually go visit it during its fleeting visit during the solar system. So that's a very exciting mission, and that's actually being led by Professor Grant Jones, who you've had a talk from previously. So just back to this graphic here now from Gaia DR2, so back in 2018. So the last aspect of astronomy that I'd like to talk about is solar system objects, and so I'm going to show you a movie of. So in green are the 200 brightest asteroids that Gaia has helped to refine the orbits of, and in pink are 4 new asteroids that Gaia has found. So the strength of Gaia is less in finding new asteroids as helping to constrain the orbits of already known asteroids and constraining those to be better. And so in particular, its vantage point from space means it can look back towards the Earth and towards the Sun a bit closer than what can be seen from the Earth. And so you can follow asteroids a little bit closer to the Sun and get more measurements to improve their orbits. And so this is important because not only to understand multifaceted families of asteroids, but also it may refine the orbits of known asteroids, and we may find out that these are actually near-Earth asteroids and potential Earth impactors. And so Gaia again may save our lives on a shorter timescale than what I mentioned previously. So yeah, on this movie they've put a bit more of a funky soundtrack. So there were 14,000 orbits of asteroids released in Gaia's second data release, but this is expected to increase up to around 300,000 for the final data release. So now we're seeing these 4 new asteroids here. And you can see that their orbits are quite different to the main body of the other ones, so they're more highly inclined. And so these are quite interesting objects to try and follow up and understand. So now we're looking in the plane of the solar system. So you can really see that the white dots show the 200 brightest asteroids, and they're mainly also in the plane of the solar system. And those pink lines, those 4 new asteroids, are actually quite inclined. So I think I was about to move on to a new movie, but I mean maybe a bit movied out. So let me come on to the. Having said you might be movied out, here's a final movie. Actually, sorry, let me just come back to this for a moment. So what I wanted to say also about the asteroids is that because Gaia is finding candidate asteroids, and Gaia only sees objects for a short period of time, because it's in a predetermined scan law. So it's scanning the sky in a very determined, pre-programmed way. So if it finds something interesting, it can't keep its eye on that object. It will lose that object as it scans away from it in this scan law. And so in which case some asteroids that are being measured are interesting to follow up. So if we know Gaia is not going to see them again for a while, and we need more measurements to help constrain their orbits, then a team of astronomers within Gaia have set up a ground-based follow-up network to follow these asteroids. And so they're asked for anybody to get involved. So I think they say typically it's for maybe the more serious amateur who's got a 1 meter diameter telescope or so, because these objects can be quite faint. So they're typically at the fainter end of Gaia, so 20th magnitude or so. But if you'd like to get involved, then there's plenty of information on the web about that. And there's also in the transient nature of Gaia, it also sees stars and other things going pop in the night. So this next movie is going to show you all the transient objects that Gaia has found. So they're transient in the sense that they are non-repeating in nature. So there are lots of variable stars, which I'm sure many of you are familiar with, that will vary in brightness in a very predictable way, and will do that periodically over and over again. So Gaia is also observing those, but because it's continually scanning, it will come back and see those objects again and again, and so we get very good measurements for variable stars. But when we have a transient object, for example, a supernova going off, Gaia may be fortunate enough to catch part of the light curve, so part of the sequence of measurements, so part of the brightening of the supernova and then the dimming. But typically, a supernova light curve will disappear in about a month, and that can be and the period of time between observations on Gaia can be longer than that, and so it may just see this object once and then not again. And so, but there's a lot of interesting science to be done by following up these supernovae and getting and following their brightness down until essentially they disappear. And so there's another network organised by astronomers within Gaia called photometric alerts, and they ask the public, so amateur astronomers and school children, to get involved to follow up interesting objects. And so again, there's a lot of information on the web on how to get involved. And in particular, school children have been able to get involved through a network of telescopes which dedicate their robotic telescopes, and they dedicate some of their time to allow school children to use them. And so they've been used by various school children around the UK to follow up on Gaia alerts, and they've been able to produce their own light curves of supernovae and actually contribute to published papers. So this movie is going to show little bright spots of all the transient objects that Gaia has found. So typically when they're in a line, this will show the scanning of Gaia. And so most of these are type 1a supernovae, which of course are very interesting to study when we're talking about the universe. So finding these objects are very, very useful. And there are also various stars in the plane of the galaxy, so various rare phases of stellar evolution that are being captured as well, and also microlensing events where objects have their brightness magnified by objects passing in front of them that are not seen. And these can be very interesting to follow up as well, which I think some of you have actually. I had a look on your website, and I think I've seen you've done some microlensing follow up. And so Gaia is the third most productive transient survey as well. In terms of producing alerts, so typically it's about they're producing at least a handful of alerts a day of different brightnesses. So there's always an opportunity to do some observing if you have the time and the telescope. So I'll finish on my this is my penultimate slide to hopefully convince you, if you haven't already been convinced, that Gaia is causing a revolution in astronomy. So on the y-axis here is the number of papers. These are published papers in peer-reviewed journals, and on the x-axis is the year, and the top performing space mission has been Hubble since 2000. So lots of other missions that you may have heard of below Hubble, and including Gaia in the first couple of data releases. So our first data release was in 2016, and then so we get having papers published in anticipation of that first data release in 2016. And then we get this large uplift when the data in 2016 became available. And then that lift has continued, that upward trend has continued in 2018, which is when the second data release occurred. And so because more and more data is being published, around 4 papers a day are being published using Gaia data, which is an incredible rate, which makes Gaia the most scientifically productive spacecraft, at least at the moment. So we've got to continue this trend to make it, in terms of aggregate, to make it the most successful spacecraft ever and try and beat Hubble. So hopefully this trend will continue up. But this is based on the hard work of all the engineers and who built the fantastic spacecraft, and all the software engineers and astronomers around Europe who are processing the data, and all the scientists who are using that data and producing some fantastic science, of which I've shown you just a few highlights. So I'll finish here. So I've hopefully I've convinced you that Gaia is revolutionizing most aspects of astronomy, but it's not finished yet. So distances are really the key to this revolution. Europe is a world leader in space astrometry. I may not have mentioned previously, but this is a European Space Agency only mission, so there's no involvement of other space agencies. And I've given you 2 examples of how Gaia may even save our lives. But if you remember one thing, maybe from this talk, is that the stars move, and they move in an interesting way that's kept me out of trouble for the last decade. And also Gaia is producing alerts that anyone with a telescope can follow up. So we've got the solar system objects and the photometric alerts. So there's plenty of ways to get involved in this fantastic mission. So I'll finish there. So thank you very much for your attention.
Thank you very much, George, and fantastic talk. And if you could hear the round of applause, it would be very loud, because this has covered a number of areas of astronomy. You know, not just mapping the Milky Way, but lots of other fields which have benefited from Gaia. So that's amazing. So there are already some questions in the Q&A, which I'll come to in a minute, and also people are asking questions on YouTube. But I just wanted to ask one question for a start. So you mentioned Oumuamua and Borisov, which have very interesting interstellar visitors to our solar system. So can Gaia actually detect those as well as sort of looking for the star systems that they're coming from?
So I think potentially, yes, I think they can. In that Gaia is basically measuring everything brighter than 20th magnitude. So if it transits our focal plane, then there's a chance it will be detected. So Gaia is expecting. So it's been designed to detect stars. So those stars are drift across the focal plane in a nice sort of linear way. They've anticipated being able to detect asteroids, as I mentioned, and so there's a special settings on board that can trace asteroids that will move more diagonally across the focal plane than the stars, because they may have because of their motion within the solar system. So I don't actually know whether interstellar objects would move in a particular way that would mean Gaia might miss them. there's also Gaia is also tuned to detect point sources. So if these objects are actually quite close and resolved, then Gaia would actually miss them. So we're detecting quite faint asteroids that appear point-like, because everything's been optimized to detect stars which are point-like.
Yeah.
But it's a good question. So yes, I don't actually know, but I imagine other surveys are probably are more attuned to finding.
Sure.
Yeah.
Yes, absolutely. Okay, great, thanks. So in the Zoom Q&A, so the first question there is from Simon Cairns. I thought it takes a huge mirror or lens to measure small angles, but Gaia is not so large. How does it measure position so accurately?
Well, so it's so the principle is actually, so yes, you're right that the mirrors aren't very large. They're about 1.5 meters long and half a meter tall. So actually rectangular. So and there's two of them, and they're separated by what we call the basic angle, which is about 106 degrees. And this means we can look at stars in one bit of the sky, and then 106 degrees we can also see simultaneously another set of stars, and those are both projected simultaneously onto the focal plane, which is quite an unusual setup. And then we're able to, and then it's being able to measure the angles between the stars in the two different fields of view that allows us to do the very accurate astrometry. So it's so it's not so much the size of the mirror, but it's the setup of it that allows us to measure those angles effectively.
Okay, great, thanks. Okay, so another one from Zoom. So Stephen Karp asks, how far away are the most distant stars whose motions are characterized by Gaia?
So that's a good question. So we are measuring stars in the very bright stars in the Andromeda galaxy are pretty much the furthest ones away. So that is what's that? We're talking megaparsecs there, I think, aren't we? Or are we? No, I've forgotten my distances. I'm sure it's but so so Gaia's as I said before, so it's measuring everything down to a particular brightness limit, which converts in a non-straightforward way to the distance that it can measure. So very distant stars in the Andromeda galaxy, if they are intrinsically bright, such that they are brighter than our 20th magnitude limit, then we will see them. Conversely, we can have objects very close that are actually, for example, brown dwarfs that are very close to us that are actually fainter than that 20th magnitude we will miss. So probably the Andromeda galaxy is about the furthest we can see.
Okay, great, thanks. So Stephen Sargent, who's a previous president of the SPA and currently a vice president, he says the gravitational lensing by solar system objects is just utterly beautiful. We've come such a long way since Eddington's solar eclipse expedition in 1919. The amazing movie you showed was the model correction. And I guess the model is very well constrained, not just by the average effects of the entire Gaia catalogue, but also by many, many individual astrometric shift detections at high statistical significance. So with all that superb data, has there been an analysis of any deviations from general relativity?
That is a good question. So I know that they're in the pipeline. So for example, I think they are looking for them, and I think there's an experiment involving Jupiter's quadrupole that is that may detect something to do with deviations from general relativity. But so I'm a bit out of my depths in talking about this, as this isn't my area. So
fair enough.
I think yes. Keep your eyes peeled for things on the future. But it's definitely a capability of Gaia to see that.
Yeah. Okay, great. And yes, and of course there's the big data release coming, so I'm sure we'll see a lot more. So again from Zoom, so is from J Walk. So is the parallax measured relative to the spacecraft or the stellar background?
So it's so it's measured essentially relative to the background. So we fix our reference frame on very distant quasars. So I didn't mention this, but Guy is also seeing many distant quasars and galaxies that appear point-like. So if they're brighter than this 20th magnitude limit, then we see those. And so the quasars are not meant to move, and so we assume that they're fixed, and that is our fixed background against which we can measure these motions, measure the relative parallax angles.
Okay, great. And actually, a related question on from YouTube. So Catherine Grimes asks, "Are you measuring more as you are measuring more and more stars? They must be further and further away. Will you have to use extragalactic objects for your background?"
So yes, we are moving. Yes, so we've used essentially used quasars from the beginning. In fact, yeah. And so and in terms of the data, so the data has been pretty much the full amount of astrometric data has been available from the second data release onwards. So in terms of how far we can observe, we've pretty much got there with the second data release, astrometrically speaking, and photometrically as well. So now with future data releases, it will be about collecting more data and reducing the size of the uncertainty on those measurements. So it's slightly different with the radial velocities, because as we go fainter and fainter with radial velocities, we actually need more and more data just to be able to make the measurement at all. And so that means so that's why we're going stepwise. We're going fainter and fainter with the radial velocities, because we actually need to accumulate the data to enable the measurement for those future data releases.
Okay, great, thanks. And Catherine also asks, how well do the stellar velocities match the models of dark matter? Very interesting.
That's a good question.
Yeah.
So yes, basically everything. There's no evidence, I don't think, in the Gaia data which suggests that dark matter doesn't exist. So dark matter is the halo which we think the galaxy resides in, and it's as the name suggests, invisible matter that's basically telling the stars in our galaxy how to move. And the idea. One of the ideas behind Gaia is to try and use these velocities to try and infer properties of dark matter, and as we get more and more data, then we hope to be able to do that. But yes, everything is looking as though dark matter is required. Rotation curves of how stars, the speeds of stars as you go further and further out from the galaxy, all require dark matter. But so we need to push the analysis more and more to try and infer about the dark matter. So yeah.
And again, more to come, I'm sure, actually, on that. Yeah, good stuff. Thanks. And then Jack Martin's got a few questions. So first of all, is there a catalogue of spectra, and what is the resolving power of the spectrometer?
Good question. Yes. So the not yet is the answer. So the spectra from the radial velocity spectrometer is going to be released in next year's data release, and we're expecting around 1 million spectra to be released. So that's quite a small subset from what's available. So we're expecting around 30 million radial velocities to be released, suggesting that we've got 30 million spectra, but we're just releasing the representative million from those that have been well characterized and analyzed by other groups within Gaia, and the atmospheric parameters of those spectra will be available as well. So the resolving power of the spectrograph is 11,500 typically. So it's sort of a medium resolution spectrograph, and the combined spectra will be slightly less than that. So the individual CCD spectra are obtained at that resolution, but the combination of the spectra for the final data product actually degrades that very slightly. So it may be sort of more like sort of 10,000 or so, but we're still characterising that at the moment.
Okay, great, thanks. And Jack also asks, what is the wavelength range of the spectrometer, and also what software is used to reduce the spectra?
So the wavelength range is so it's 846 nanometers to 870 nanometers, or 8,460 angstroms to 8,700 angstroms. And the software has been all developed. It's all been it's all bespoke. It's all written in Java. So we weren't able to use existing packages to reduce the data, as can be used for various ground-based spectrographs, because the challenges of reducing the spectra that come from this instrument mean that a lot of bespoke solutions are required in order to successfully reduce the data. So there's a whole list of issues that we've had to overcome that don't exist on ground-based spectrographs, and hence the need for a bespoke solution for each of those.
Okay, thanks. So there are a few more questions on Zoom as well. So first of all, was it this survey that determined that the Milky Way is a bar spiral galaxy?
That is a good question. I think it may have been probably infrared data that allows you to look through the dust, or in fact the dust that you can see obscuring the central bit of the galaxy in the slide here, means that Gaia isn't probing the positions or velocities of stars very close to the center of the galaxy. So the extent to which we can get there may be providing supporting evidence for the bar. But I think the strongest arguments for the bar probably come from other surveys that can peer through that dust. But then in terms of spiral arms, so there are so we're now so the 7 million radial velocities have been used to start to map out the spiral arms, and so there is more and more evidence about the nature of those spiral arms from the existing data.
Fantastic. Okay, thanks. And maybe finally, so how is the age of stars factored into the results, given that light takes some time to get here, and we're essentially looking back in time, not seeing distant stars as they are now? So it says, apologies if this is a stupid question, but it's not. And
no stupid questions. No, it's a good one. So so we don't really need to worry about that. So I mean, I'm thinking of the Monty Python song, the galaxy being 100,000 light years across.
Yeah.
So when we're looking at stars from the other side of the galaxy, it takes 100,000 years for that light to get to us. But the typical lifetime of a star is much longer than that. So, for example, our sun is just over 5 billion years old, and so the light travel time to get to us is not an issue in terms of stellar evolution, which is much longer. But I mean, there are occasions when the light travel time is more important, and maybe within particular microlensing events, timing exactly when something happens, that could be more important, and perhaps also with objects in our own solar system, with asteroids, the exact timing and that delay between the measurement and when it actually happened, you could imagine that would be more important.
Okay, excellent, thanks. And there's another question about dark matter. I think you've answered that. So, and then actually, finally, so if Planet 9 exists and is brighter than magnitude 20, will Gaia detect it?
Ooh, interesting. So, yes, in principle. So there've been quite a few surveys that go as faint as Gaia. So in particular, ground-based photographic surveys have gone that faint and haven't seen Planet 9 or Planet X.
Yeah.
So I think that yes, the chance, but so I don't. So I guess my guess would be that it's probably not very bright if it exists, because we probably would have seen it in other surveys at some point. But if it's essentially a dark object, then maybe the best bet is through an occultation. So from this object passing in front of stars. So there, the Gaia dataset is sufficiently rich, and the positions are extremely well known, such that you might be able to infer its presence from that. Yeah, it's a good question. I don't know if anyone's thinking of doing that, but
yes, interesting indeed. Yeah, that's great. Okay, well, thanks, George, again for such a fantastic talk and for answering all those questions. And as you can see, there's been a lot of interest, and both on Zoom and YouTube. So thanks again, and particularly nice, with your great grandfather, was it, or great grandfather, having worked on it, and only to discover that during your PhD as you're doing your literature survey, I guess. And
I know, yeah, it's a bit freaky in some ways.
Fantastic, yeah, and but really well explained talk, and really fascinating, and as I say, very broad across different parts of astronomy. So much appreciated. Thank you very much. And
thank you to everyone listening, and for all those excellent questions.
Yeah, thanks a lot. Okay, so now thanks again everybody for the interest, and to George for the fantastic talk. And so now we have a sort of 10-minute break, and after the break, Robin Scadgel will talk to us about the night sky, and we also have a talk by Mark McIntyre as well. So in the meantime, so we'll start again at 3:35, and thank you again, George. Thank you.
Thank you.
Thanks. Okay, so welcome back, everybody. Hope you've all managed to get a cup of tea or whatever. And so the next part of the afternoon is continuing with, first of all, Robin. Robin's scheduled to talk about the night sky. So go ahead, Robin.
Okay, thank you very much. Now, everyone else seems to share their screens so quickly. Let's see if I can do as well. That's not the one I want. Let's start with presentation. Not there yet. It's not the first slide I want to show, actually. There we go. Should be seeing the whole screen now, is that right?
Yes, that's perfect. Yeah, thanks.
Good. Okay, thanks very much. Now, sorry, this is a bit dark. This is the sky as it will look tonight, more or less. And I'm going to be talking about the sky as it will be visible over the next few 3 months, basically. Now, even if you can't see much of the sky there, I must say I need to brighten up my view as well. Let me just do that. You'll need to brighten up that one if you can't see too well, if you're looking on a laptop like I am. But the key thing around the moment is the planets Jupiter and Saturn. And of course, this is really a great time to start looking at the sky, if you haven't already done so, because, well, right at the moment, the moon is coming out of the way. It's going up to last quarter. It doesn't get into the sky until just about after midnight. So do keep a lookout. And after this talk, we've got Mark McIntyre coming up to talk about the meteor showers, which you can see. So I will avoid talking about those. So there's the sky as it is roughly at the moment. Jupiter and Saturn, you just can't miss. And they're down in the south. And early in the evening, this was the timing of this picture is actually about 23:38 in the evening, as from the south of England. And there's a significance for this time because that is the moment at which astronomical twilight ends. Now, we don't normally talk about twilight and worry about it too much, but actually during the summer months it's quite important. Now, in the London area, astronomical twilight on the 1st of August tomorrow ends at 23:37, and that's pretty well the time that I chose for this. This is the moment at which it gets properly dark and starts again at 02:26. Now, the thing is that you don't get to see much of the sky. You don't see the whole sky properly until that time when astronomical twilight ends, which is the moment at which the sun gets 18 degrees below your horizon. Now, I said this is for the London area, or south of England, roughly speaking, from you somewhere. But as you go further north, then, of course, it gets darker. The summer skies in particular stay very bright. And we in the London area, we're getting 2 hours, nearly 3 hours of proper night. But if you go up further north to York, for example, even now, the 1st of August, astronomical twilight ends at 1:03, just after midnight universal time, and begins at 01:17. So the sun is only for a quarter of an hour below 18 degrees of the horizon, the northern horizon in that case. So you only get 14 minutes of proper night in York. And if you're up in further north than York, you don't get proper night at all at this time of the year. Well, the thing about this coming 3 months is that this is when everything changes very rapidly. And what's more, it's when the conditions are quite mild still. Hopefully in August, they will be quite warm and comfortable for observing. And even as we go through to September and October, things will still be quite mild compared, for example, with the winter or even the spring. And it's no surprise that this is the time of year when the astronomical star parties start to take place, and at various sites such as Kenning Heath and Kielder and so on. I think they have star parties, maybe down in the Isle of Wight. I'm not sure if they're all taking place this year. I know that the Kenning Heath Equinox Star Party is taking place in October, and it can be quite mild. It's not usually too cold. As we go towards the end of the, towards the middle of our period, by September the 1st in York, you get nearly 5 hours of darkness, proper darkness throughout the night. And as you go towards the end of this period we're talking about, the next meeting will be on the 30th of October. And by that time, proper night is from, we're talking even about in York, it's from 1932 in the evening to 6:03 in the morning. So you get 10 hours of darkness throughout the, this is proper darkness, not just a sort of, not twilight. So that's a point to consider when you're observing. These things happen very rapidly from now on. And if you're looking at the movement of the sun across the horizon when it sets, you will find that it moves quite quickly from night to night as well. Surprisingly quickly, actually, compared with midsummer, where it hardly moves at all in terms of setting point. So there's the sky view. Now, I mentioned Jupiter and Saturn. Let's talk about those a bit more. At the moment, this is the view as they are at the moment, and you can see Saturn is well in the middle of Capricornus there, showed the borders of the constellations, and Jupiter at the moment is in Aquarius. But because this is the time of close to their opposition, they are actually retrograding in their orbits, and the Earth is moving faster than they are in their orbit, so they will actually appear to move backwards along the ecliptic. Now, Saturn's at opposition on, well, in a couple of days' time, on the 2nd of August, and that means that that's when it is more or less due south at midnight. That is midnight universal time, or midnight or 1 o'clock BST, and it will be being so low in the sky at the moment. It's about 20 degrees altitude, something like that, even at its highest. You can see down at the bottom of that picture, we've got the 180 degrees mark, which is due south. And so that is just past the meridian. But on the night of 2nd of August, Saturn will be at its highest for the year, due south at midnight BST. And that's on the 2nd. Jupiter is at opposition on the 20th of August. As you can see, they're quite close together. Last year, of course, we had the spectacular conjunction, the great conjunction of Jupiter and Saturn. But Jupiter is pulling well away from Saturn now, and it will get farther and farther apart until in about 6 years' time, they'll be on opposite sides of the sky. And now this is actually on the, I think this is on the 31st of October. You'll see that the two planets are well within Capricornus, having moved well to the west of where they are at the moment. Jupiter in particular has moved quite a bit, so they're both in Capricornus. So if you've ever wondered, if you ever felt that Capricornus is a difficult constellation to find, Jupiter and Saturn define where it is during the second part of the period we're talking about. So keep an eye on those planets. As I say, a couple of days to opposition, and this is the time to look for the opposition effect of Saturn. Now, these are a series of pictures taken a few years ago by a very close neighbour of mine, Dave Tyler, lives literally down the road from me, and he is a foremost astrophotographer, takes some brilliant photographs. And here's a sequence he took with his, I think it was 14-inch Celestron. And the actual opposition, as you can see on the caption there, was 15th of June 2017. And he got a shot on the 16th, and then he got a few, some clear nights. So you can see that on the 16th of June, there's a considerable difference in the appearance of those planets. The one at the top, just a day after the actual opposition. If you look on the 13th and on the 17th, you can notice that the very bright ring, ring A there, is ring B, is very bright indeed. As you go farther away from opposition towards the 20th, then the rings, that bright ring tends to have much less brightness than the others, and Saturn takes on its more normal appearance. Why is this? It's one of the reasons we know that the rings of Saturn are composed largely of ice particles. And You know, if you're driving along and you're looking at the cat's eyes in the road, they really reflect back the light from your headlights. The light comes straight back to you, just as it does from a genuine cat's eye. And that's what's happening. There are internal reflections within the ice crystals in the rings of Saturn, which doesn't happen if they were solid particles. Being ice crystals, they can reflect, totally internally reflect, and the light comes straight back to the sun. The sun is literally behind our backs, as it were. And when we're looking at Saturn, when it's at opposition, the light is reflected from the ring particles of ice, more or less back in the line of sight. And you can see the enormous difference it makes just as a matter of a few days. So if you can look at Saturn in the next day or so, you will see that the rings are very bright indeed compared with the planet. And Dave has tried to normalize the pictures compared with the globe brightnesses there. Jupiter has actually, I meant to relabel one of these. The one on the right should be July 2021. These pictures were taken of Jupiter by Larry Todd, and he's living in New Zealand. He's a member of the society the opposite side of the globe. And this shows you the enormous change in appearance of Jupiter that's taken place in the last few months. Now, the appearance on the left in 2020 shows the planet as it has been appearing for many years, with the darker the north and south equatorial belts, and in the middle a somewhat muted equatorial zone. Still got some tone in it, but not nearly as dark as the belts there. But at the moment, you can see that the belts have reduced in brightness. They're still dark, but the equatorial zone has changed colour and is certainly more noticeably dark than either of the other two belts. So that is something well worth looking out for. I know that Jupiter, I'm not a great Jupiter observer myself. I was gazing at it in the sky just last night, and it's really quite well up to allow you to make some reasonable observations, which it hasn't been in the last couple of years when it's been so low in the sky. So do take a look at Jupiter through any telescope, and you will notice this considerable difference compared with what we are used to. So that's Jupiter for you. Now, another thing to look out for, and this shows you the view of the sky in the early morning, and this is tonight's view. And you'll see in the middle, this is I don't usually show these views from Sky Map because they can be a bit sort of muddling compared with the rather pretty views from Stellarium, which are rather nicer to see. But this at least shows you graphically what's going on, and it's a brighter view compared with Stellarium. There's the more or less the last quarter moon in the center of the field there. It seems to be labeled Uranus, but that's not Uranus. Uranus is the small dot just above the letter U, I think. So the moon and Uranus are quite close together, but I don't think you can use the moon to find Uranus. Uranus is a lot fainter. But we're looking at the constellation of Cetus here, and this is how to find it. This is looking more or less due east, and you've got Perseus up to the quite high up in the east. Andromeda and Square of Pegasus are even higher up. You'll probably recognize those. Aries in the middle there. If I can see my cursor, there's Aries, not labeled for some. Oh, yes, there's a label. And below that, we have got the constellation of Cetus. Now, there's the constellations lines drawn in, and you can see it's a bend there where there should be a star, but it's not shown. And that is the location of the star Myra. If you like, the two lines of the constellation of Pisces, the two fishes, point straight to it, but that's not a very good guide. Those are quite faint stars. There's something you have to find for yourself. But Paul Sutherland was photographing this area of sky just this morning and took this picture here, which shows the situation that you'll see. This is an enlarged view. The view from right to left is about 25 degrees. These are the one end of Taurus here, and that is what we call the head of Cetus, the sea monster. And if you can find that, or you can find Pisces, or you can find Taurus, or find Aries right up there, you need to navigate, do a bit of star hopping to find this part of the sky. And there is the star Mira, which I'm sure you all know is named Mira, the wonderful star, the first variable star to be identified in as such, which I think was in 1596 by David Fabricius. And this was regarded at that time as absolutely amazing. This was at a time when things in the celestial heavens, the celestial spheres, weren't meant to change. Tycho pointed out that the comet of 1572 seemed to crash through the celestial spheres, and this wonderful star that appeared more or less proved the point that there was a star changing when it shouldn't be, because he noticed that Mira was invisible at some time and really quite bright at others. And now is the time, at this during sometime in August and September, it is reaching its brightest. So if you want to find Mira, that's the place to look. And you can see it's considerably brighter than this star Alpha Ceti, which is about magnitude 2.5. And so it is getting quite bright. Sometimes it doesn't brighten up anything like as much as this. So it means an early start to find this star. But if you want to find Mira at its brightest, then now is the time to look. So that's what's coming up, and some things for you to look at. Normally I would mention meteors, but we've got, stop share. We've got Mark coming up as well. So why don't I just hand over to Mark now? There's no, I'm sure you all know that Mark is our meteor section director, and look, he's got some meteors behind him as well. So let me hand over to Mark now, who can tell us what's coming up in the next few months in the meteors. I think you're muted, Mark.
Yes, there's always something you forget, isn't there? So hopefully you can see my screen and hear me now. So yes, I'm going to talk a little bit about what's coming up on the meteor front. Obviously, we're coming into the best part of the meteor season. But before I go into the talk, I'm just going to tell you a little bit about the picture that you're actually looking at. Some of you may recognize this already, but this is the image of the Winchcombe meteorite that I got on my camera. And the reason that I'm talking about this now is not because it's a great photograph, because I don't think it is, but it's because we were looking pretty much straight at that event as it happened. And so we saw it end on. And that's going to be relevant to something that I'm going to say in a little bit about meteor hunting. So just bear in mind that picture. All you can see is really big flash, maybe a little bit of maybe you can see a bit of where you think the trail of the meteor might have been, but basically just a big flash. Okay, so for those of you who don't know me, I'm an astronomer and astrophotographer based in Oxfordshire. I'm the SPA Meteor Section Director, as Robin has said. I'm also a member of the UK Meteor Network and the Global Meteor Network. And these are video detection networks that are generating meteor detections using video cameras. And the Global Meteor Network in particular is generating data that's used for scientific research. And I'm going to slightly plug the Global Meteor Network here, because we actually have a paper that's just about to be published in the monthly notices of the RAS, looking at the data that we've captured so far, and a bit of the methodology that we've got, and some of the discoveries that we've made. For example, the network has found a couple of new meteor showers, which I think is pretty exciting. And this data also helps us find meteorite falls when they happen. So anyway, coming back closer to home, as probably most of you know, the meteor hunter's calendar is very much a game of two halves. The first half of the year is pretty quiet. There's a shower in January and there's another couple of showers in April and early May, but up until the end of June, there's not much happens. And now things start to kick off in July and August. So already active, we've got the Capricornids, the Delta Aquariids, and the July Pegasids. Those are minor showers, but they are already active. And obviously we've got the Perseids coming up in a few weeks. And toward the end of the period I'm going to talk about, we've got some more showers. We've got the Taurids, the Draconids, and the Orionids, and some more minor showers that I'll mention briefly. So what about the Perseids? Well, we all know the peak of the Perseids is the 12th and 13th of August. And there's a picture showing where the radiant is. For those of you who are not aware, the radiant is the point on the sky that it looks as though the meteors are coming from. They're not actually coming from that point. Of course, we're just interacting with this debris stream as we pass through the solar system, but that's where it looks like they're coming from. As it turns out, the Perseids are actually active from the middle of July right through to late August, and in fact, we've already started picking up Perseids on some of the video detection networks. UKMON has already picked up over 1,000 potential Perseids, and 101 that we've confirmed by calculating their orbits. So it's already active. They're already happening. We're picking up a few dozen a night across the network, but as I say, the peak isn't for a couple of weeks yet. Now, when people talk about the Perseids, you'll see the newspapers in particular will say rates of up to 100 an hour. Now that's what's called the zenithal hourly rate, and that is the rate if you had perfectly clear skies, not a cloud to be seen in a dark sky site, the radiant was directly above your head, and you could see the whole sky at once. Now, we're human beings, we can only see half the sky, so these numbers always need to be divided by 2, I'm afraid. But that's the quoted rate that you will see. So round about midnight on the night of the peak, the radiant will be high in the east, in the northeast, sorry. And this year we're really lucky. There'll be no moonlight to get in the way. That's actually quite unusual. Moonlight seems to blight most of the meteor showers that I try to observe. I just mentioned a minute ago that the quoted rates of 100 are probably very optimistic. Realistically, if you're in a reasonably dark site and you've got a clear sky, you probably see 50 to 60 an hour. And remember, again, those numbers are averages. We are actually currently forecast to have a clear night on the night of the peak. So, cross fingers, things at the moment are looking pretty good. Perseids are fast moving, which can be quite useful diagnostic. We also tend to see more fireballs from Perseids. There is a bit of a tendency to create fireballs. They're also quite often colourful, particularly in photographs. You'll quite often see green in the tails and sometimes orange in the bodies. And you'll sometimes also see an ionization cloud left behind, particularly by the brighter ones. I'll explain a little bit about how you can spot that in a moment. So if you're thinking of doing some visual observing of the Perseids, here's my essential guide to how to do that. So you can see on the right there's a picture of my meteor hunting equipment. It's a deck chair or a garden recliner. You need to be comfortable so you can lie back and look up at the sky. You don't want to be sitting on an ordinary garden chair and craning your head up to look up. You'll want to keep warm because even in August it's going to be cold at 2 o'clock in the morning or 3 o'clock in the morning. So a blanket and hot drink is probably a good idea. I'm fortunate enough to have this lovely space blanket that was made by my mother-in-law to keep me warm in my meteor hunting exploits. And you'll also want a notebook or a clipboard or something like that to keep some notes of your observations on. Now, I've mentioned the radiant, and you might think that that's the place to look to spot the meteors, but actually it's not. If you think back to that picture of the Winchcombe meteorite that you saw at the very start of this talk, like I said, we were looking straight at that meteor when it happened. And so all we see is a big flash. And it's the same if you look at the radiant of a meteor shower. All you'll see is head-on meteors coming straight toward your eyeball, and all you'll really see is a flash or maybe a very short trail. So the best place to look is off to one side, usually kind of 45 degrees off to the side. If you get the radiant kind of in the corner of your field of view, a bit like this picture is arranged actually, then you'll be looking at the meteors as they go across in front of you, and you're much more likely to see nice long trails and bright events than you will if you're looking straight at the radiant. So that's a top tip for any meteor shower. Always look away from the radiant. Choose the side of the radiant that's going to be darkest for you. For me, that's normally the north, because we've got Oxford to the south of us, so I would look north. But obviously just think about your sky conditions. If you want to take some record of your observations, then this is the method that I normally use. It's very simple. I just write the time and the date across the top of the page. And then each time I see a meteor, I make a mark on the page. Every hour, I turn over to a new page. And then at the end of the night, I can come in and I can really quickly just count up how many meteors I saw per hour, and I can get an estimate of that hourly rate. If you want to get more experienced, you can obviously use the form on our website to add a lot more detail, like you can add color that you saw, the constellation you saw it in, how bright you think it was by comparing it to nearby stars. But as a beginner, the best thing to do is just that simple record. I actually use the clock in our village to time when an hour has passed. It chimes on the hour, so I can use that to give me an estimate of time. But you can use an egg timer, or you can use the mobile phone or whatever. But if you do use your phone, remember the screen is probably going to come on when the alarm rings. So you'll want to figure out a way to reset the alarm without ruining your night vision. If you do take a report, then please do send it in to me at meteor@popastro.com. I always collect all the reports that I get together and include them in the section reports that appear in the magazine and then later on the website. If you do send a report in, it's good if you include the weather conditions as well, just so that we have an idea of how much cloud was obscuring your view and that kind of thing. And there is also on our website, if you see a fireball, there is a reporting page for reporting fireballs. So a minute ago, I talked about seeing the color in photographs of Perseids in particular. And I wanted to talk a little bit about photographing the Perseids, or indeed any meteor shower. And the good news here is you don't need an expensive high-end camera to do this. I'm actually using a budget Canon EOS 1100D with the stock lens that came with the camera. So it's nothing fancy. But what you do need is a camera that can do manual focus, that you can manually control the ISO and exposure time. And it also needs to be a camera that you can set into continuously taking photographs, because you're going to want to just leave it running all night. So if it can accept a remote shutter cable or an intervalometer, so you can just lock it in with the shutter open, taking photographs all night, that's what you need. The other thing I'm going to say here is shoot in JPEG. Now, I know that most astronomers will normally shoot in RAW, but you don't need that for meteors. They're bright objects, and RAW files take a lot more space up. Now, if you're going to be imaging for several hours at 10-second exposures, you're going to get a lot of pictures. And so you don't want to fill your memory card up with raw data. So shoot in JPEG, it'll write to the disk faster, it won't fill up the space, and you should get more pictures. As I said, I use the stock lens. I've got an 1855 stock lens that came with the camera. Actually, a wide angle lens can be counterproductive. And the reason for that is that meteors, particularly the faint ones, will be lost in a wide angle lens because of everything is that much smaller. So, 18 mil seems to work pretty well. You do obviously want the F number to be as low as possible to get as many photons in as you can. I mentioned a shutter cable or intervalometer and a sturdy tripod so you can keep the camera steady while you're imaging. The other thing, if you're based in the UK, you're almost certainly going to need a dew heater to keep your camera lens from fogging up. It depends a bit on the weather conditions. I think actually for the night of the Perseids at the moment, the dew point is going to be pretty low, so we might be all right. If you do want to make a dew heater, I'm going to plug my wife's article in Sky at Night, where she tells you how to make one with simple objects. So have a look at that article if you're interested in making a dew heater. So fit the dew heater to the lens if you're going to use it. Focus on a bright star. Robin mentioned earlier on that Jupiter and Saturn are well placed. They'd be good focusing objects at the moment. Get your focus as tight as you can. Take a few test shots to see that the exposure and ISO are good for your sky conditions. I live in reasonably good dark skies here. These settings work for me. You may find that if you live in a light polluted sky, you need to change the settings a little. Or if you're lucky enough to have nice dark skies, you may find that you can expose for longer. But exposure length isn't really critical. If you do too much exposure, you'll get too much of the background sky coming through, and it will actually hide the fainter meteors. The other thing I would say about photographing is have a think about the framing of the shot. Now, a meteor can look fantastic in a picture, and I'll show you a few pictures in a second. But it can look even better if there's something interesting in the foreground, like a church tower or a farm building or the lights of your village twinkling in the valley below or something like that. That sounds a bit romantical, but you get the idea. So have a think about whether you can do some framing to get something interesting in the foreground to just, as much as anything else, give you an idea of the scale of the meteor. If you just take a picture of a meteor, you've got no idea how big it was on the sky. But if you've got some buildings in the foreground, then you can really get an impression of how big it was. And that can be useful. As with visual observing, don't point at the radiant, point off to one side, set the camera up, lock the shutter cable so that it's taking constant pictures, and try to leave it alone. There'll be a temptation if you see a bright meteor flash through the field of view to want to check on the back. But I mentioned earlier on about the debris train or the ionization train that you sometimes get from a meteor. Now, if you fiddle with the camera and review the pictures, you may miss something like that happens in the few seconds or the few minutes after the bright event. So try to leave the camera to do its thing and then review everything in the morning. You can sit there over breakfast flicking through 2,000 pictures trying to find the ones with meteors in. So these are some sample pictures. These were all taken with the Canon DSLR that I just mentioned before. Nothing fancy here. This is a slightly cropped image taken by my wife, Mary, in our back garden. And instead you can see the green in the end of the tail here. Maybe there's a bit of orange in the middle. It depends on the settings of your monitor, I suspect. This is another one that was taken in our back garden, again with the same equipment. And again, you can see those colors. Now, neither of these has got anything in the foreground, so it's very difficult to gauge how big that meteor was on the sky. This was taken quite early evening in the garden in Oxfordshire, and you can see here I've got some trees and the hill in the foreground. So you get a bit more of an idea of the scale of the object, how big that meteor was when we saw it in the sky. And this last one here was actually taken near Bulthwells in South Wales. Mary and I normally go to the Solar Sphere Music and Astronomy Festival when it happens in South Wales. And this was taken after the main event of the had finished. We were sitting out on the hillside with our cameras set up. And you can see here that Mary's got some trees in the foreground. She's got the asterism of the plough, giving you an idea of the scale and sort of majesty of that fireball as it flashed through the sky. And again, you can see the color and the structure of it a little bit. So that's the kind of thing you can get with just a fairly standard camera. As long as your camera can do manual settings, then you should be able to achieve something similar to this. And I did mention ionization trails earlier, and this is a good example of why you shouldn't fiddle with the camera if you can manage to avoid it. So this is again from our back garden, the bright fireball that shot through the sky, and after the fireball had passed, you can see, if you look closely, you can see there's a little bit of cloud evaporating away from behind it, and that's the ionization that I was talking about. That's debris from the meteor that's just sort of evaporating away into the sky as over a period of time. Now, this short sequence is about 25 minutes worth of data. So these things can last quite a while after the main event of the meteor. And that's why I say you should leave the camera to be. If you're tempted to look at it, in fact, Mary did review the pictures on the camera here. And you can see, because there's one point where the stars all double up. And that's where she knocked the tripod. So, you know, if you're imaging and you see something like this, always have a look at the frames immediately after the fireball to see if you've picked up something like this ionization trail. Because that's pretty special, I think. Okay, I've talked a bit about the Perseids and I've talked a bit about how to image, but I thought I would finish up by talking a little bit about some of the other showers that are coming up later in the year. The first one I'm going to talk about is the Draconids. Now, there's two reasons I want to talk about the Draconids. And the first is that you'll notice that the period over which they're active is very short. Now, when I talked about the Perseids, I explained that they're already active, and they're active now for the next probably 4 to 6 weeks. Most meteor showers are active over quite a period of time. If you think back to the calendar that was visible on the first picture I showed, and is also on the website, the bars are quite long. They're usually active for 2 or 3 weeks. But the Draconids are active really for 4 or 5 days. And they've got a sharp peak on the 8th. Realistic rates that you might see for this shower is about 2 to 3. And they're very slow moving, which makes them easy to pick out from the other meteors that you might see around. The other advantage is that there's no moon this year. The radiant, if you're wondering where that is, that's near the box of Draco. So it's pretty much due north and it's circumpolar, visible all night. The other reason that the Draconids are interesting is that they sometimes experience outbursts. And I've put a number here. That sometimes the outbursts are really significant. You can get up to 700 as an hourly rate. But the thing with outbursts is they don't last very long. So most outbursts last 5 to 10 minutes at the most. And in those outbursts, you might see 60 meteors in 5 minutes, and that would be something special. Now, is there's no forecast of an outburst this year, but the thing with these outbursts is that they're unpredictable, and so who knows, it might happen. So if you're out observing the draconids, you may be lucky and see an outburst of this nature, and if you do, please do tell me about it. I'll be very interested to know. The other two fairly large showers for later this year are the Orionids and the Taurids. Now, the Orionids, unfortunately, are going to be blighted by moonlight this year. There's a nearly full moon is nearby on the peak, which is on the 22nd of October. Realistically, with the moonlight around, although the quoted rate is 25, 2 to 3 is a more likely rate. The radiant is also very low down, and so that means we lose a lot of the meteors which are going below the horizon, and so that changes the hourly rate too. So really, I'm not expecting much from the Orionids, but if you have clear skies, you please do go out and look. They're quite fast meteors, similar in sort of speed to the Perseids. The other shower, or the pair of showers, I should say, that's active in the latter half of the period that we're looking at are the Taurids. Now, these are 2 streams of debris left behind by Comet Encke, and they're active. They don't really have a peak. They're active throughout most of October and some of November, and so the advantage there is that although the moon will be affecting some of that period, there'll be periods as well where moonlight's not affecting them. And again, you could expect to see rates of 2 to 3 an hour from that. There are a couple of minor showers as well that I'm going to mention, which are coming up a bit sooner than that. The first of these is the Alpha Aurigids, which takes place at the end of August and start of September. Peak rate for that, again, will be about 3 per hour. The radiant's going to be low in the east. There will be a little bit of moonlight, which will affect that. So that will be a tough one to spot, I think. The other one that takes place in this period is the September Perseids, which, as you can see, the radiant's near the foot of Perseus. And that will peak on around about the 9th. So the moonlight won't affect that so much. Again, a rate of about 3. So these are both minor showers. If you're out and about, and you see some potential members of these showers, please let me know. And I'm going to conclude just by reminding people about sporadic meteors. So we've talked about the shower meteors, and of course these are usually pretty spectacular, but we are bombarded constantly. We're bombarded constantly by shower meteors. You know, every night we're being hit by them. And in fact, about 70% of the meteors that we detect on the UK Meteor Network are sporadics. And so no matter what night you go out, if you sit and look up, you're likely to see meteors. My cameras pick up a dozen at least every night on each camera. And sporadics, of course, include this one. Now this, as I'm sure you recognize, is the Winchcombe meteor that happened back in February. You know, I was saying back at the start of this talk that the first few months of the year are super quiet for meteor hunting and really nothing much happens. Well, sporadics happen all the time. And this is another good example of why you don't look at the radiant. If you think back to my picture of this event, I was looking straight at where the meteor was coming from. So all I see is a big flash. This picture was taken from off to one side of that track. And so it's a much more spectacular, much more interesting picture. And so that's why you don't look at the radiant, although obviously sporadics don't have a radiant. And that's it from me. If you want to know more about any of these showers or any of the other showers that are happening over the next few months, there is lots of information on our website. There's also information about how to set up your cameras. If you're interested in the video detection or the radio detection, there's information about that there too. There's information on my own website. And if you are interested in the video detection, then the UK Meteor Network and the Global Meteor Network websites both have more information too. And with that, I'm going to hand back to Robin.
Thanks very much indeed. Would you like to stop sharing your screen? Actually, I should be handing back to Andrew, who's the chair of the meeting. I sort of segued into Mark there, but Andrew, if you'd like to take over now.
Yeah, well, thank you very much to Mark, and thank you very much to Robin for 2 excellent talks, and meteors and Robin's quarterly update on the night sky. So fantastic, and so that really, I think, concludes the meeting for today. Actually, I'll just check if there's any questions that have come up. So the links to the articles have gone into the chat. Oh, actually, there was a question from John Murrell. Anyone heard about EZ Aquarius? We got an alert from ZTF today. The images look very strange and it has to be unable to measure the magnitude. Don't know if anybody knows about that. Robin, have you heard of that?
Not something I'm aware of, no, but it's on the, if you want to read what John has said, it's on the YouTube chat. Anyone heard about EZ Aquarii?
Yeah.
Alert from ZTF, I don't know what that is, to be honest.
No, not
so that's something for you to research if you're into variable stars, because EZ Aquarii is a variable star.
Absolutely. Okay, well, thank you very much again, both to Mark and to Robin, for excellent talks, and also, of course, to George for the talk earlier. Really good talks today, and thank you very much. So the next meeting is going to be, the next quarterly meeting will be on the 30th of October, and Susie Imber will be talking about Mercury, the first rock from the sun. So she's involved in the Bepi Colombo mission, so we look forward to seeing that talk. So thank you very much to everybody, and thank you to Dave in the background for actually doing the making sure the IT works and so on. Thank you all, and have a good evening and clear skies. Thanks.
Bye, everybody. Bye.
Bye.